Good afternoon, everyone. So this week we will talk about counting. I believe this is the first time we talk about counting for this year. So we want to quickly review, or for those of you who never learned about counting, to talk about some fundamental concepts about counting, especially from the perspective of Mathcounts and AMC, those competitions. So what is counting about? Well, counting is really some very, very basic thing in math. And the extended application about counting is we will study probability. And in some sense, you have somehow learned a concept called statistics. Well, rigorously speaking, statistics is a branch that is based on probability. But so far, there's some just kind of misleading concepts about statistics, like the average, the mean, and the mode. Those concepts. Then you learn statistics. That's actually quite misleading. So statistics is a very, very, very important branch of mathematics and has many, 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 many significant applications in life. But that's something really far down the road. You don't have to worry about it until college. But for middle school math competition or high school math competition, you will need to just really know some very basic things about counting and probability. And what is counting? Well, everybody know how to count if I give you the numbers 1, 2, 3, 4, 5, right? That's the very first thing you learn in life about the mathematics. Even before you learn how to write down those digits, you just need to count things correctly. That sounds trivial, but things can quickly become complicated. Actually, in my opinion, among the 4 major areas in middle school, high school math competition, algebra, geometry, counting and probability, and number theory, counting could be the most difficult one. Most students feel geometry is, but that's only because geometry is not taught the right way in America. If you really learn geometry in a conventional way, you will see at least all those AMC, Mathcounts, geometry problems are really trivial. They don't ask you to do any proof. So that takes away a huge part from geometry. Counting, on the other hand, it seems simple, but any problem with just a little bit twist, the nature of the problem will get changed. And it could be surprisingly difficult. So you know how to count 1, 2, 3, 4. So let me give you a very quick example. Let's just say we have 1, 2, 3, 130, 137, 144, 151, and so on, until you hit say something like 7,000. Let me just do that. 7,151. How many numbers are in this sequence? And first of all, you need to understand what this sequence is, right? This is so-called arithmetic sequence because it doesn't take too long for you to see that the difference between any 2 adjacent 2 numbers, the delta or the difference is 7. How do I know I will hit the last one? That is exactly in this sequence because I didn't count, but I figured that this one is 7,000 more than 151. Therefore, this one is 1,000 steps away from 151. So by that, if I cheat, I will know there will be 1,000 numbers after this guy. And right now we have 5, so I know the total is 1005. But that's only because I gave you a very convenient number, cheating on myself to figure out what that valid number could be in this sequence. If I give you another one, then it may not be that obvious. But what is the general trick to count the numbers in this sequence? Well, then you need to understand, because this is an arithmetic sequence, you want to somehow transform this sequence into a much easier to count. Because fundamentally, you need to figure out a way to map this sequence to something like this. Like 1, 2, 3, 4, and in this particular case, this will be 1005. Okay? Why is that? Because from the very nature of arithmetic sequence, there is such an underlying mapping. But how do you figure out how to do the mapping? Well, apparently, if you map 1, 2, 3 to 123 to 1, the next one is 7 more than that, and the next one is another 7 more than the first one. You see that you need to first adjust each number by some kind of a big displacement to get rid of the effect of 1, 2, 3, which has nothing to do the differences, right? So naturally, you want to subtract 1, 2, 3 from each of the numbers. Then let's call this sequence as AN, where N starts from 1. So AN minus 7, that's the first transformation. Then you get this sequence to something like 0, right? 7, because you are subtracting the very first one. So every difference will become a multiple of 7. So clearly, you get something like this. Okay, this guy would become something like, let's just write that. I don't want to compute right now. Okay, so that's something about it. And clearly, you see this sequence is something you feel what the fundamental nature of this sequence is about. So that's quite close to this, but still not there yet. What do? At this time, you can divide this by 7. Then you can get another one like a 0, 1, 2, 3, 4, right? This is much closer. So if I divide this by 7, now you get something. And now you see that the difference is only 1. Then I just add 1. Okay? So that's the transformation you need to go from here, which is an arithmetic sequence, to a really conveniently countable, that's a natural number sequence. And that's the conversion. Of course, from this step, 0, 7, 14 to this, you can either divide 7 by first and then add 1, or you can add 7 first, then divide it by 1. It's the same thing. So, I'm sorry, that was typo. This should be 1, 2, 3, not 7. Okay. Initially, you write subtracting the first in the sequence from every other number. So this is the final formula for you to transfer information from the original sequence to the final sequence. How do I do that information transfer? I convert the original sequence into such a counting sequence. That's called transform. And the formula is using the very first one in the sequence, and then the distance between any two adjacent number, then get result divided by this distance. So in general, you have a arithmetic sequence that is AM with a distance D. How do you convert that into the natural number sequence? The general formula you can see is an minus a1. That's the first step, so that you get something like a 0, 7, 14. And remember, at this point, the very first item in the sequence is 0, because a1 minus a1 is just itself. So after this step, you get a sequence like a 0, D, 2D, 3D. That's the sequence you get. So now you add everything by D. That's the distance. Effectively, you shift this by D. So this is 2D, 3D, and so on. Now you know if you divide this by D, you get 1, 2, 3, 4. And that way, you just look at the very last one. Whatever result you get after this transformation, that will be the number of the total items in this sequence. And that is the general trick for doing this kind of thing. So you can see that counting is actually quite just convoluted if you think this is already not that obvious. But this is perhaps the easiest, the simplest counting. All the other counting problems will be significantly more difficult than this. So that's what we will try to study today. But before doing that, let's consider counting at a very high level. What do we need exactly to do from a philosophical perspective? Well, we need to get an accurate count of certain numbers or certain items following a certain constraint. We need to count things exactly. What does that mean? We cannot overcount. We cannot undercount. Right? Yeah, what do you mean by count things exactly? You cannot count more than what the numbers should be, and you cannot count less than what it should be. That means there's no overcounting, no undercounting. Why do we have overcounting? You count something more than once. That's the only possibility for you to overcount. On the other hand, what could be undercounting? Well, you skipped someone. Some items you should count, but for whatever reason, you did not count it. Then undercounting may appear. You may say, well, I do both overcounting and undercounting and somehow cancel each other and still get it correct. Yeah, you are lucky if you happen to cancel out the same numbers, then you commit both overcounting and undercounting, you get the correct answer. Lucky you, but that was not the way it was supposed to. So if on the other hand, if you guarantee you never overcount and never undercount, you count everything once and exactly once, then you will get a correct number, right? You count everything once and exactly once. That is exactly what counting should be. You count everything once and exactly once. Therefore, you don't have overcounting, you don't have undercounting. Your final count will be exactly what you should get. So, two principles. No overcounting and no undercounting. That's something you should always keep in your mind. Okay? So that's counting in general. Let's look at today's problem. The very first problem actually is a very challenging one. Okay, but it illustrates a lot of important points in counting problems in general. So we have a 5x5 grid here. All the dots, right? And equally spaced, either vertically or horizontally. So how many different squares of any size can be formed by connecting 4 of the dots in the grid? So we know square means that you have equal size and equal angles. Each interior angle is 90 degrees, so we know what that means. So clearly, if you need to find a square by 4 dots, then that's kind of symmetry. It's kind of, because square is such a nice figure, it has a lot of symmetry. You have horizontal, vertical symmetry. You also have central symmetry, meaning that if you rotate this by 180 degrees, it gets back to yourself. So immediately coming to your mind is that in order to avoid undercounting, you can quickly find out the regular way of, say, 1 by 1, 2 by 2, that kind of square we see in this figure, which is the 2 horizontal sides are horizontal, right? 2 vertical sides are vertical. But before you even count, you should consider something like, if you rotate this a little bit, this could be still there and it's legit. For example, if I have 1, 2, 3, 4, 5, it's not perfect, but it makes point. If I say I just connect this diagonal, right? Then this will be obviously a square because you rotate it a little bit. So you should immediately recognize that you must consider things like this. Otherwise, you will have undercounting. Okay? But how many such kind of just less obvious cases are there? Well, you should investigate a little bit. When we have such a rotated square, what is exactly going on? Remember, each side of the target square is still connecting 2 dots. Then you should recognize that whenever you connect any 2 dots within this figure, essentially either it's a horizontal one or vertical one or somehow diagonal one, although it's not necessarily a 45-degree diagonal. So for example, if I just connect those 2 points, what happened? Well, you can see that this is connecting a triangle, which is 1 and 2. One side is 1, the other side is 2. So this is square root of 2. So now you can figure out that not only consider typical ones like horizontal and vertical, you have to consider all possible radical form where the side is the hypotenuse of a triangle. Okay? Not everyone is valid, but you have to consider all the possibilities. For example, if I connect this dot with this dot, well, this one is right there, but you cannot form a rectangle because you do this. Now I need an extra dot from here. It will go outside. I don't have this dot. I don't have this dot. So if you choose an initial diagonal like this, apparently it cannot be formed within the grid. So some are valid, some are invalid. That's the key of doing this problem. So now, next let's go through how we do it. Well, in this case, it's something called casework. What does casework mean? Casework is a very basic and very important, perhaps the most fundamental techniques in counting. That is that if you want to count certain things having certain properties, I want to break that general case down into subcases and then count each subcase and then add all those numbers up. If I did casework correctly, then I will be able to get the total. So this is a wonderful problem illustrating a lot of points. What does that mean, breaking down a property into subcases to do casework? Well, I will consider for the property, the general property that I'm pursuing into several different subcases. And the point here is that when you break down that general case into subcases, you have to make sure that you get everything covered and there's no overlapping. What does that mean? Let's consider a concept. So if I have something conceptual like space, I want to, this is a rectangle. I want to break this space into multiple parts. How do I do it? Well, let's just do it arbitrarily in some way. I break this space into how many parts? 1, 2, 3, 4, 5, right? This is a perfect partition of the scene because in this case, what I just did, I partitioned this space into 5 parts and covered every possible tiny area of the space. I did not leave anything, say, I leave out a certain thing uncovered. If there's a hole here, then you are not doing the correct thing, because if your partition does not cover this green area or this area, then you have not covered every possible cases because you left out some holes there. So that cannot be allowed. On the other hand, there's no over counting, meaning that if your partition say it goes here, then 1 and 2 overlap a little bit, overlap by this much. That's not allowed either, because in that case you will have an overcounting problem. So if you want to break a total case into subcases, you have to cover every possible case, meaning that if you combine all those subcases, they should cover exactly the original overall case. And there's no overlapping. So in other words, all those subcases are mutually exclusive. They cannot share anything in common. They have to be completely separate from each other. All right? So if you can achieve both, you cover the whole thing completely, and there is no overlapping between any two subcases, then that's exactly what we said earlier. No overcounting, no undercounting. You count everything once and exactly once, nothing more. So that's the logic behind this. In actually, if you do just an individual count, 1, 2, 3, 4, that's also a special subcases. That's just a brute force way. You break the whole thing into each individual case and you count one, all of them, 1, 1, 1, 1, 1. You add all of them up. That's another special case, but that's just too tedious and not something that we want to do. So this is kind of just a compromise somewhere in between. I divided the whole problem into smaller problem, but not so small down to the each individual case level. So that way, I just need to count how many numbers. In this case, case 1, case 2, case 3, case 4, case 5. Then I just add those things up. Then I will get the total count correctly. So if I add all them up, this will give me the total count S. So that is subcase. Okay, so now let's consider what we can do just for this problem. Well, obviously we want to first count the low-hanging fruit one by one, right? Because this is a 5 by 5 grid. How many 1 by 1, meaning horizontal and vertical lines are perfectly lined up? Well, that should be 16, because you can easily see there are 4 by 4, so there are 16 such cases, meaning that we have 1 by 1 cases. The next one would be 2 by 2. Well, it's not too difficult to see that in order to get 2 by 2, you will connect things like this, and because you can shift it in certain way. So you can shift it, and then you can see the same thing down here. So total way of forming such 2 by 2 squares would be 9, because the first one is 4 by 4. Now your square grows one bigger in the sides, then the possibility will go down, becomes 3 by 3. And then if you have 3 by 3, that will be even bigger, and your choice will be even less. So in this case, it's easy to see you only have 4 cases, which is 2 by 2. So this will give you 2 by 2, 4 possibilities. And finally, if you go to 4 by 4, that's just the whole thing. You connect the 4 corners. That's the only way to form this. So clearly, that's just one cases. Okay, so we cover 4 subcases, and we did it correctly. There's no overlapping. Apparently, it's impossible you find any overlapping case. 2 by 2 is 2 by 2. 3 by 3 is 3 by 3. They can never be the same. So, and you count each one correctly. But we are not done yet. Now we have to count all other diagonal cases. Let's just say if the 1 and 2 sides are 1 and 2, what kind of diagonal you have? You have square root of 5. So it's better you initiate this process systematically, then count each one. You can just say, I want to count all the square root of 5 side squares. It's okay to do that too, but it's it's easy to lose the big picture when you do that. So I personally think it's a better idea. Say, I see 1 and 2. 2 and 2 is something that we have not covered yet, so we have to cover that as well. So this will give you, what is 2 by 2? That will be 2 square root of 2, right? Because this will be square, but the side is an irrational number. Remember, we are talking about diagonal, the hypotenuse, not the simple 2 by 2 case. Okay, those smaller ones seems very possible, but if you consider, if we go very big, say 4 by 4, can you do that? That would be 4 square root of 2. Obviously, that's even bigger than the original, the biggest grid right here. That's impossible. So you have to eliminate at some point. So you have to try whether each one is possible first. So square root of 5, that's obviously possible, because this way you can get that, and you can get that. So it's obviously possible. I'm not drawing it perfectly, but you can see. So this is possible. How many there? That's another thing. We have to, because there's another rotation. It's kind of symmetric. This is really symmetrical, right? So that's another way to get a square root of 5 one. But for now, let's not go there yet, because it can easily mess up the grid. So it's 2 by 2 and 2, so that the diagonal is 2 square root of 2 possible? That is possible. But this case, you can see this is as big as you can go, because this will be a 2 square root 2 side length. And this, without just too much thinking, you can see this is the only possible way to get this. This is already stretching to the 4 sides of the big grid. And if you just move this a little bit or rotate this a little bit, you will have to go outside the original grid. So that quickly set up a limit. This will be the maximum you can get in this case, but there's still some others. Like say it's 1, 3 possible. If you get 1, 3 as the right triangle size, then you will get square root of 10, right? 1 plus 9, that's square root of 10. Is that possible? Yes, indeed, this is possible, because if you, this is a square root of 10. In this way, you can easily see it just exactly how you can get there. There is such a way, right? No more, no less. You just like the 2 square root 2 case, you just put all the 4 vertices on the 4 sides. That's just, you're stretching to another limit. You cannot go bigger, but you cannot go smaller. But is this the only one? Well, obviously not, because you can rotate whenever you have this, because you can get a just a symmetrical one right here. And that's another way to get another such square root 10 just squares. But how many are there? Well, you can see that essentially that depends on where you choose this one. This vertex, if it's here, you get 1, because all the other are rotationally symmetrical. It's the same, but you can also pick here. So there are actually just 2 of rows right there. So then you have to count all the other cases. So we know this one, the square root 2 square root 2 case, give us exactly 1. And the square root 10, how many? We see we have actually 2 cases, because this will give us exactly 2 squares. Either choose this point or choose this point as a vertex. All the other 4 sides are kind of centrally, rotationally symmetrical. We don't have to worry about this. Then this guy, square root of 5, is a little bit troublesome. This is kind of just, you have to consider, if I start here, then the other side must be here. So how many of rows? Well, we can start here as well, because that way it will go this direction, right? So this one really creates some problems, but it's not that difficult to see. Essentially, if I get rid of, this is perhaps the most challenging one. Let's recover all the orange dots. So this one is the most challenging one to get the accurate count. How many square root of 5 rectangles are there? Well, you have to look at how many such choices. Let's choose, say, the vertex is here, because in that way you will see that you will get 1 starting here. Then you rotate, you get 4, right? Because of this, you can see that there are immediately 4 possibilities, because this one will be also possible. It just kind of draw symmetry here. If this is the axis of symmetrical axis, then whenever you can choose here, you will get here. It will give you a rectangle, a square, I'm sorry. So that way we can see that 1, 2, 3, 4, there are 8 such choices, but you need to be very careful not to overcount, okay? Overcount can happen if you really get just everything counted twice. So that way you can see there are actually only 4 of rows. But you can go actually inside by shifting, say, if you have something like this, you will go this way. Okay, this is interesting, because this way will not, the 2 vertices on two sides, but this is the middle one, and this is a one inside, not just the four sides, not like what we did earlier. So you will be able to see by rotation, if you do it carefully, you will have four such squares. Just say the two sides here are completely inside, and this is also inside by shifting a little bit. So you will actually see in those cases, you also have four such squares. In total, therefore, the square root of 5 side squares, there will be 8 of them. Because I cannot just draw all of them, it will become messy, but you need to be very careful. You will be able to see that's the total cases. So in this case, if you have square root of 5 squares, you will get 8 in total. And how many such cases in total? You just add all those things up. Okay? So 4 by 4, you have 16, 9, 4, 1, that have 14, 16 plus 4, that's 29 plus 10, that's 10. So you got 40 in those nice cases. So then in this case, you can see that finally you will be able to count all. Hold on. Oh, there's one more. Okay, there's let me see. Yeah, there is one more case. 1, 2, 3, 4, square root 5. There's a square root 2 cases we forgot to mention. That's an even bigger problem. So there's a square root of 2 cases, right? We forgot a 1, 1 case. That's why you need to cover everything carefully. We forgot to count these cases. This actually is even, will give you even more, but this one is relatively simple because 1 by 1 is a nice diagonal. You can see that you can shift this to any point as long as it does not go out. So there are actually 9 such cases. Okay, so inside this, yeah, because of difficulty of drawing this thing, so I did not do a very good drawing. So for example, this is a square root by square root 1 by 1, 1 square root 2 cases. You can see that if you shifted this, then you will be able to shift along each direction 3 times, right? This is a 1, 1, 1, 1, 1, 1. So that's the only 3-way shift in this direction. Similarly, you can shift in this direction. So it's also 3 times. So the total number for square root of 1 is actually 9. Okay? So then you just, at the end, you just need to add all those things up. You add every possible subcases up. So this is 16 plus 4, 20, 9 plus 1, 30, 8, 2, 40, 1, 9, another 10. So at the end, the total is 50. Okay, so this is a very difficult problem, but the principle is actually quite simple to understand. You break it down your general cases, which means that we have to find squares into all the subcases. And there are 2 categories of subcases here. So one is horizontal and the vertical one is a diagonal one. Then you have to be super careful, list each subcases. So 1 by 1, 2 by 2, 3 by 3, 4 by 4, that's a horizontal and the vertical case. Then we have to investigate all the possible diagonal cases. And we figure out both square root 10 and the 2 square root of 2, those are the kind of just a maximum you can get because they already stretch to all the 4 boundary sides of the grid. You cannot actually go beyond that. If you do, then you will go outside the grid. So those are kind of the limiting ones. Then you have to figure out within that limits, what kind of side length you can get. One is square root of 2, one is square root of 5, and you have to carefully figure out for each subcase how many squares without duplicates, without overcount anything, how many are there. And it turns out that for square root 2, you have 9 possible ways just because of our shifting. You can shifting is twice, get 3 in each dimension. So it's a 3 by 3 count, you get 9. And square root of 5 is that you can rotate a little bit, so you get 8. Okay, so that way you get the final count, that is 15. So it's very easy to mess up with this problem because you have to consider all the cases. And within each subcase, you have to count accurately without any duplicates, without any overcounts. So that way, we will solve the problem. This is a very difficult problem, but it does help us illustrate a lot of principles underlying a counting problem. Okay, let's move on to the other problem. We spent so much time on this problem because it is the most difficult problem of this week. So, how many collections of 6 positive odd integers have a sum of 18? Note that the sum, those two are the same because it's just a different order. So now we get it. We want 6 integers. They have a sum of 18. So on average, each one is just 3, right? So meaning the numbers cannot go too big. Otherwise, it will quickly get, say, over the 18 limit. So how many rows collection? By collection, so the order doesn't matter. So that's why rows 2 are essentially the same. They're the same collection of integers. So how do we count this problem? Well, in this case, we go again through the casework strategy. The challenge is here is how to break this case, which is kind of constrained. I have 6 numbers and they add up to 18. There's no order considered. How do we break this general case into some subcases? Well, essentially we will do something later we call constructive counting. That means that how to build this case 18. Then we think about maybe we will just try those numbers. And because each number on average cannot go bigger than 3, that's just average. So probably we want to start with smaller numbers. How about if we say all the numbers are just 1? Then we try as many 1 as possible. So we try 5 ones, then we get 1. We will have to have a 13, right? So we get, if we have 5 1, that will be 13. So this is one case. If we get 4 ones, how many numbers we can get? 1, 1, 1, 1. Now, if we have 4 ones, we have a budget remaining as is 14 because total is 18. We have 2 numbers to add up to 14, but we cannot have another one because we already consider 5 1 case. So meaning that we can have 2 other numbers, they add up to 14, and the smallest will be 2, so that will be 2 plus, because the total is 14, 2 plus 12, 3 plus 11. So you can quickly see that when you hit 7 to 7, that's the max you can get. If you go over that, remember if you go to x plus 6, but you already have 6 plus 8, the order doesn't matter. If you consider 8 plus 6 and 6 plus 8 at the same time, you have an overcounting problem because you count essentially the same because twice. You cannot do that. So if we only have 4 ones, the total possibility in this case is 4. because you have 4 ways to fill up the other 2 without having 1, but the total is 14, give you the total 18. Total 18. So that we covered. Okay, so if 4 ones, we get 4. Now, how about if we only have 3 ones? Well, since it becomes a little bit more interesting, now we need to add up to 3 numbers. They need to add up to 15, right? Now, the total is 15. This is the goal. You add 3 numbers to 15, and you can start with some 2s. Okay, so that way you can have. We will follow the same strategy. Start with the smallest. If we start with 2. If the smallest is 2, and we try to be as small as possible, you will have 2, 2. We will have 11 here, right? Okay, exclude 2, 2, then we'll have 2, 3. Now you see, essentially, we fix the first 2. You want to see how the other 2 numbers can add up to 13. So 3, 10, 4, 9, 5, 8, 6, 7. That's about how far as you can go. Because if you go over it, it will be 7, 6. Then essentially, it's the same thing. You will have an overcounting problem. So with 2 as the smallest number, you can have 1, 2, 3, 4, 5. But remember, this is just a temporary count because we have not considered what if the number go beyond 2. So let's start with the smallest number as 3. In this case, the total remains 15 to add up to 11. But now with the smallest 3, following the same strategy, if this is 3, the second smallest is again 3. Now what is that? So you just get 1 less than this. So it will have to be 9, right? 3, 3, 9 is 15. That's the current total budget. So 3, 9 is possible. 4, 8 is possible. 5, 7 is possible. And finally, you have 6, 6. So in this case, you have a sub case that is 4, meaning that you have 3 ones, and the smallest one is now 3. You have 4 cases. We covered the sub case 2, starting with 2. Now, if it's starting with 3, you get those 4 cases. Now we start the smallest as a 4. So now you can see 4, 4, 7 is allowed. 5, 6, that's about it. You cannot go beyond 5, 6. Otherwise, you will have duplicates. So in this case, you have 2 sub cases. And finally, if you start with 5, how many there? Well, this one only gives you 1. That's the only way you can add up, because the now smallest is 5 other than the 3 ones. And the total must be 15. So there's only 1 possibility. Okay, those the sub cases, because we were considering the case where you have 3 ones. And now we see this is a 5, 4, 2, 1. Well, you need to add all of them up. That is 12, right? So you add up to oh, hold on. I'm sorry. I think I committed a mistake. Odd numbers. Okay. So in that case, we got a lot of problem. See, that's why we need to be very careful when we read the problem. It's the odd numbers, so our county has a lot of, actually it should be not that many. I'm sorry, my apology. We have to go back to the earlier cases, but it's not that difficult to figure out. We only have odd numbers. We cannot have any even numbers. So with 4 ones, we will have we have to add up 14, so that would be 3 plus 11 and 5 plus 9 and 7 plus 7. So that actually gave us 3 cases for the no, this is no, with 5, with 4, this is 1. With 4 ones, we can only have 3 plus 9, hold on a second, no, 3 plus 11, 5 plus 9, and 7 plus 7. So these are actually 3 cases. Yeah, this is actually simpler than what we just do. So this is 3. And if you have 5 starting with the smallest one now, then it cannot, 5 and 9 is already covered. So you only have 2 numbers. So in that case, it's just a 3. Okay, with the case, you have 3 numbers, then this thing is not something like this. We have to redo this. So you start with 3. 3 plus 3, because you need to add up to 15, right? The goal is 15. The next one would be 9. Okay, this is possible. Then 3 plus 5, this will be 7. And finally 5 plus 5 plus 5. So in this case, it's once again 3. Okay, so that's the subcase for you have 3 ones, because I made a mistake. I count all the even numbers, forgot that the problem says that you can only have odd numbers. That actually makes the problem much easier. So now with 3 ones, you have 3 cases. The next stop would be consider only 2 ones. In this case, you have to add up to 16, right? The total has to be 16 because you have 1. But because all the numbers are even, all the numbers just must be an even number in order to get 16. If you have odd numbers, they add up to an odd number. So in this case, you need to have 3, 3, 3, and 7. Yes. And then you can have 3, 5, 5. No, this cannot work. 3, 5, 5, you will get over because this will be 18. So the only way to get this one would be 3, 3, 7. And there's a 5, 5 case. Okay? So that way the count would be 2. You cannot go beyond that. So in this case, 2 ones, you have rows 2, which generate a 2 count. And the last case where you only have 1, now you need to have 5 numbers that they add up to 17. Once again, you start with the smallest one, which is 3. So you start with 3. We try as few as possible. 3, 3, 3, 3. That's 12 plus 5. That's about it. It's quite easy. You can see that this is only one case. You cannot have anything bigger than this, because the next one, if you change to 5, then 5, 5 will go over the limit. So if you only have 1, 1, this is the only way. 3, 3, 3, 3, 5. Okay, finally, we cover the case. There's no 1. All right, because we start with how many ones you can have. We have 5 ones, 4 ones, 3 ones, 2 ones, 1 1. And then we have the 0 1. What does that mean? You have to start with 3, right? In this case. But we already said the average is 3. if the small is 3 and your total is only 18, obviously you must have everyone as 3. And you don't have anything else. Therefore, in this subcase, you again have just one case. So, did we cover all the cases, subcases? Yes, we did. This is exactly how casework works, because we focus on what the smallest number 1 we can have. We figure that we can have 5 ones, we can have 4 ones, we can have 3 ones, 2 ones, 1 1, and 0 1. No one at all. In that case, every number needs to be 3. So essentially, those 6 subcases are complete. They cover all cases, right? You cannot have anything else. And they don't overlap. But the key is that for each subcase, we have to count things accurately. This problem is not that difficult in terms of enumeration, but if you see that if we remove the constraint that all the integers, if all the integers, even integers are allowed, the problem could be much harder, and the counting principle still works. We just need to be very careful to break down all the possibilities, then add it up. That may sound like a tedious, but in many cases, that's perhaps the most effective way doing counting, unless you have some other strategies, which in cases we haven't seen, it is possible. But in this case, this breaking down of the system is very effective because we have the constraint, only odd numbers are allowed, therefore we can quickly get to all those cases. Okay, so you will see that that's how we get the total count. So 1, 3, 3, 2, 1, and 1, you just add them all up, okay, to be perfectly accurate. So when you have 5, you have 1 here, you have 3, 3, 2, 1, 1, 3, plus 3, plus 3, plus 2. So the total in this case is 11. Remember, we have a case here, right here. This is 5 ones. You don't have anything. So this is 2 ones. This is 3 ones. And this is 5 1, 4 1, 3 1, and this is 2 1, 1 1, and 0 1. Okay, so they add up to 11. So this is a relatively easy problem. I'm sorry I waste some time, but let's move on to the next problem. Well, this problem is actually kind of the same nature. On the grid below, draw all the lines with integer y-intercepts and slope 1 or negative 1. Okay, the line form many intersection points. So how many of these intersection points lie in the interior of the shaded region? So we have a shaded region with the horizontal measure is 2 and the vertical 3. So this is a 3 by 2 rectangle. So the just in slope 1 or negative 1. So you have to understand what that means. So on a coordinate plane, slope 1 just means a line of 45 angle like this. And negative 1 slope is just in this direction, right? So so the guy Beatrice drew all such lines with such and you have to do the y-intercept is an integer, meaning that you have to passing through all those, this kind of just thing, going through all the integer lengths. Okay, that means that the rows lines form many intersection points, and you count how many rows intersection points inside the interior of this triangle. So the easiest way to do this problem is going through the just actually do it. Okay, so let's just count that. So we actually do the 3 by 2. Be very careful in terms of drawing. So let's do all the 3 by 2. So essentially this is the 3 by 2 1. So we just do this through an experimental thing. So we draw all the, start with here, use the green pen. So this is 1 intersection, and this is another one, right? And this is another one. Remember, the intersection must be completely inside this 3 by 2 matrix. So we can do the same thing on the other dimension, this -1. So that's how you actually generate all the lines. So how many intersections do rows lines have? Because the next one will go beyond that. You will not be able to do anything. So rows are all the lines you will be able to draw. How many intersections are in this red rectangle? You just count them, right? So 1, let me use this one. So 1, 2, 3, 4, 5, 6, 7. And there's one more here. Forgot to do this one. So, okay. So that's how many intersections you will get. Okay. So 1, 2, 3, 4, 5. There are 8. Okay. So this is a very brute force approach to this problem, but it's small because this rectangle is relatively small. So you can actually do that. But if this is very big, say 20 by 10, then you will have to figure out a formula for this. There is a formula, right? You can see that there's certain rules, like the intersection could be integer or somehow half integer, right? This is half. So you need to figure out a formula. It's actually not that difficult because you don't consider any boundary cases. Rows intersections are not counted. So rows are not. So you just need to figure out all the true interior point. So if it's 20 by 10, I think it's straightforward to count how many in each half line like this, and all the half lines and also the integer ones, and then you can figure out the formula. But for such a 3 by 2, you just brute force count them. Okay. All right. So that's what we will do here. This number 4 is a very classical counting problem. A bag contains 10 identical blue marbles and 10 green marbles. How many distinguishable ways can 5 of those marbles be put on in a row? So 5 distinguishable in a row. If there are at least 2 blue marbles in the row and every blue marble is next to at least one other blue marble. Okay. So you have 5 blue and 5 green, I believe, right? Or 10, each 10. So 10 blue and 10 green, but you put them into 5 slots. The constraint, you just figure out how many ways you can meet this condition. How many distinguishable ways can 5 of those blue put in a row? 5 of those 20 marbles put in a row. there are at least two blue, and every blue must be next to at least one other blue. So you just focus on blue, right? It doesn't really matter how many greens. The 10 doesn't really matter because you just need to figure out how many this combination there. So why don't you just figure out based on the blue case? Remember, the constraint is that at least two blues, okay? And then each blue cannot need to be at least adjacent to a blue. So the obvious case is to say how many blues are there. So case 1, let's consider all the blues. Everything is a blue, 5 blue. How many ways there? Well, you just have one case. Everything is 1, right? Well, if we have 4 blues, how many can be there? Well, if we have 4 blues, we have exactly 1 green. And where is that green? We meet this constraint, we have at least 2 blue, but each blue must be adjacent to another blue, so the green cannot be here. It cannot be here either, because if we put the green on either one, there's an isolated blue in the other slot because it's separated. So the blue could be, the green could be here. It will not separate anything, could be here. And it could be in the middle. That way you have blue, blue, green, blue, blue. So that way we meet all the conditions. So if we have 4 blues, we have 3 possible cases, right? Because that makes sense. Those are the greens. Green, green, green. Those 3 greens. That's 4 blues. If we have 3 blues, what happened? Well, once again, because all the blues have to be next to at least 1 blue, the 3 blues, we cannot have 2 at one location, the other get separated. So that way, the other lonely blue will break our rules. So in this case, actually, it's quite simple. All the 3 blues must be together, right? So that means that you have blue, blue, blue. The 3 must go together like a block. So in this case, how can you position that block? Well, obviously, you can start as this block. You can start there, and then finally you can be there. So all the possibilities are exhausted. So with 3 blues, you must have a block like this. And there are only 3 possible ways to put that 3 blue block. So again, you have 3 here. And finally, if you only have 2 blue, obviously they just like a blue, blue block. And how many ways to put that? Similar to the 3 blue block, there are only 4 positions. You just shift it through the 5 positions because they have to go together. So you have 4 cases for 2 blues. Okay, so that gives you all the cases. Okay, so if you have 5 blue, only 1 case. 4 blue, you have 3 cases. 3 blue, you have 3 cases. And finally, you have 2 blue, you have 4 cases. They add up 1, 3, 3, that's 7. 7 plus 4, so you get 11 in total. This is another example of how to do the casework, because in this case, you just need to carefully choose how you want to structure your cases. Okay, we based on how many blues are in the final construction. So this is actually another example of what we call constructive counting. Okay, so notice that actually those numbers are kind of irrelevant. Let me say I give you 6 blues, 5 greens. Does that really matter? It doesn't really matter. So those numbers are kind of just misleading a little bit. Okay, finally we have this problem. This is not a real counting problem, but we will just do some logical reasoning. Okay, so A, B, C, D are competing in the race. Eric says, see Rose comments. Actually beat both B and C. D finished between B and C. If exactly one of those is correct, meaning that if one is correct, the other must be false. So in that case, what is the correct order? Well, in case you don't know, I gave such a problem to some 5th graders this year in my free Asian math class, because this is actually, in China, grade 3 students do a lot of problems like this because it doesn't require too advanced arithmetics, only some logical reasoning. And the logical reasoning is not extraordinarily complicated. So let's just see how many exactly how many different ways of finishing are possible. Well, how do we solve a problem like this? Well, we just first understand what does those conditions mean. It means that the two are mutually exclusive. Exactly one is correct. So why don't we just consider first, without any constraint, how many possible ways of finishing the race? Anybody studying at this time you are doing Mathcounts competition, you should know that this should be 4 factorial. You have 4 people, they can finish in any order, so it's 4 times 3 times 2 times 1. This equals to 24 possible cases, right? This is without any constraint, the way of possibly finishing this. Okay, now consider the constraint. So the first constraint is actually beat both B and C. Okay, so in that case that if actually is behind either B or C, that cannot be case. So something like this. You have A, and you can have B, C, or C, B in any such orders right there. But there's only another constraint, D. If 1 is true, then 2 cannot be true. So what is D? D finish between B and C. This cannot be true. So that means that either you have D ahead of both B and C, or D is behind both D. Okay, we use this notation to know it doesn't matter. So in this case, we also use the same notation to know A is ahead of both and C. Okay, so how do we do this? This is the first. If A is true, then we will have this constraint. A is ahead of both B and C, but D cannot be between B and C. So D is either ahead of both B and C, or D is behind both B and C. Okay, so this is the first condition. If the first one is false, that means that A is kind of just cannot just at least behind B or C. But in that case, D must be between B and C. Okay, so in this case, you can either construct everything based on those 2 set of conditions, or use elimination. Okay, using elimination is a little bit harder, but it's more straightforward. So you just, because you can think about it, A, B, C, you start with all the 24 possible case. You start with A at first, so you immediately see that in this case, B and C will work. So you move on to the A, B, C, D, A, B, D, C. In this case, you will see once again this this one, D is between B and C. You will cross it out. Okay, so then you continue. So you cover all the B. You move C up, A, C, B, D. Then you can see that D is not between B and C, so this will work. But if A, so this one will work. And finally, you have A, C, D, B. Well, this one, once again, cannot work. So you will have to cross out. You can proceed in this way. This is elimination. But it's a little bit tedious because you have to list all the 24. Then you will figure out actually, so there are 12, just 12 cases cannot work, okay? So in this way, you will see that out of the 24, there are 12 cases that can work because you eliminate 12. Another way is to do the constructive thing. I say this is correct. A is ahead of both B and C. We can construct that case. Now we know this is incorrect, right? D must be either before B and C or behind B and C. So A is ahead. Then you can see that you will proceed essentially the same way, but you will need to construct all those 12 cases. So one is doing addition, one is doing subtraction. When you're doing elimination, you subtract 12 invalid cases. And when you do addition, you build 12 valid cases. Okay? So a constraint like this is quite tedious because it doesn't give you a very straightforward way, say, using the formula to get all the things. But you have to limit yourself to the constraints. Remember that the two constraints are mutually exclusive. So if one is true, D must be false. And that means that D is either ahead of B, both B and C, or behind B and C. But if 2 is true, then you will either have a sub-pattern like a BDC or CDB. So that is the second case. This is true. But at the same time, A will have to be behind either B, like a BAC or BCA or CAB, but you cannot have both of them behind. This constraint, I personally believe, is kind of hard to work with because you will have to consider all those cases. So then it's not something really can be easily just build a constructive counting. So if I do this problem, it does take a lot of time. I will just do straightforward elimination. That is it's the bulletproof. It's a little bit tedious, but it's just kind of very mechanical. You just go through the list, quickly eliminate all those invalid cases. Okay, so this problem is kind of just does take a lot of time, and the Mathcounts does give you this kind of problem, which is kind of not very interesting because there's no kind of just cleverness in it. You have to just check all the cases. Okay, so finally we have this last problem. This is once again a casework problem, but this casework problem actually much easier than you think. All right, this is just straightforward casework. So we want to count how many triangles, right? So obviously you want to start with the smallest triangle, which is individual triangles. So the first is the smallest triangle. That's something like either that or that, doesn't really matter. How many there? So 1, 2, 3, 4, 5, 8. There's 16. So this is the simplest one. This is the simplest, the smallest one you can get. Now it becomes a little bit just tricky. What is the next smallest triangle? Well, it must be 2 together, right? Something like this or this. Is there anything else? I don't see any. So if you do that, you will be able to see that you have to cover both cases carefully. So let's consider the first one. 1, 2, and there's one here, 3. And then, so on the flip side, if upside down, you have 1, 2, 3. So that will give you, I believe it's a 6, okay? So in this case, there are 6 of those triangles, okay? Then you have to consider something like what is the next possible one? You cannot have 3 of the smallest triangles to build up a bigger triangle. You need at least 4, and 4 could be something like this. Or upside down version, the same thing, but so. Okay, for those triangles, how many there? Let's consider the base is in the bottom. So that way 1, 2, that's about it. Upside is 1, 2, 3, but you have the symmetry here. So for example, here 1, 2, 3, 4. So there are 8 of those triangles right there, right? So if this is the case, you get 8. Okay? So be very careful not to undercount, because you have 1, 2, but left hand side also works. So that is 4. But flip it, you get another 4. So the total is 8. So we are counting on, we are based on our casework on how many smallest triangles inside your target triangle. So this is 1, case of 1. This is the case of 2. And this is, you have 3. So you got a 16, 6, and 8. Okay. So let's move on to the next level. What could be the next one? Well, you cannot have 5 triangles building a big triangle. You cannot have 6. The only possible way is to get 8, meaning that doubling this guy, right? If you compute, combine the 2, the fourth case is that you have 8 such triangles. So something like really big. Things like that. Okay? So how many of those triangles there? Well, apparently in this case you only have 2. That's as big as you can get, right? But we have not considered another cases. Oops. How did we count these cases? No, not yet. So we have to count this one as well. Okay, so in this case, we have really 1, 2, 3, and 4. Okay, this one will give us 4. Okay, so this is kind of just really brutal force counting, and by that we have essentially cover all the cases. Okay, it's not something you really like to do, but it's something that just you just need to be careful about all the cases. Okay, so finally this add up to 16 plus 10 plus hold on, 10. This is 36, I believe. So hold on. I think there's 2 more. Oh yeah, there's a 2 here. So this one gives us a 2. We mentioned that, but we did not count it. This has a 2. Okay, so this is 16 plus 6 plus 8 plus 4 plus 2. That add up to 10, 10, 36. Okay, so for counting problems, today we see a lot of cases where you have to be very, very careful how to break down the caseworks and not to overcount, not to undercount. That's the challenge. Okay. One final comment. I saw in some Chinese competition math books, this kind of problem generally appear for grade 3. Okay, so I don't know how they manage to do that, but they're pushing the limit a little bit too much. Remember, in America, this is for middle school kids, and in China, they do it for grade 3 kids, which is, in my opinion, not that good. Okay, I know today we go way over, and I did made a mistake earlier that waste some time, but this is our very first counting session. I hope you have not been overwhelmed. Because of that, we cover a lot of things. So, but don't worry. Later counting problems, some of the problems today are actually very hard. It's just that you have to cover all the unexpected, less obvious cases. But later, we will do something more interesting, because today we have a lot of just we don't have any clever way but to do the hard work. But sometimes it is what it is. Okay, I will see you next week. Bye.